Hello everybody, my name's Iman. Welcome back to my YouTube channel. Today we're going to be covering Chapter 8 for our MCAT General Chemistry playlist, and this chapter is all about gases. Now, understanding the physical properties of gases, especially focusing on the relationship between pressure, volume, and temperature, is going to allow us to know how to answer questions like, why does the pressure of a gas increase when it's compressed? Why does a gas expand when it's heated? And why does a gas diffuse through a room? To be able to answer these questions, we're going to have to cover a couple of objectives. First, we're going to define pressure, discuss units of pressure, and then talk about instruments that measure pressure. Then we're going to begin a discussion on the gas laws. Here we're going to cover Boyle's law, Charles' law, Avogadro's law, and Gay-Lussac's law. Then we're going to use our knowledge of the simple gas laws and express them in a way that shows a relationship between volume, pressure, temperature, and number of moles. Essentially, what we're building up to is the ideal gas law. Then our fourth objective is on gas stoichiometry. Here we're going to expand our stoichiometry toolbox and learn about liter-to-liter ratios as well as STP. This is standard temperature and pressure. We're going to follow it with a discussion on Dalton's law of partial pressures. Dalton's law of partial pressures states that the total pressure of a mixture of gases is equal to the sum of the individual partial pressures of each gas. So we're going to explore some important formulations here and work through this definition conceptually. We will also briefly mention Henry's law here. Then next up is the kinetic molecular theory, which is going to show how the macroscopic properties of gases result from the behavior of the individual particles making up the gas. Our seventh objective is going to be focused on understanding the difference between effusion and diffusion. And then last but certainly not least, we're going to briefly discuss real gases and how they differ from the assumptions we make when we're dealing with ideal gases. Now, there's a lot to cover here, so let's go ahead and get started with the first topic, and let's define some important concepts. Now, the first objective is really focused on pressure, but I still want to define temperature and volume here. Temperature is defined as a physical quantity that expresses how hot or cold something is. In other words, it's a measure of the average kinetic energy of atoms or molecules in the system. Volume is defined as a scalar quantity that expresses the amount of 3D space enclosed by a closed surface. And pressure is defined as force per unit area. Let's elaborate on this. Now, a gas is going to uniformly fill any container. It's easily compressed, and it's going to mix completely with any other gas. One of the most obvious properties of a gas is that it exerts pressure on its surroundings. So, for example, when you blow up a balloon, the air inside is going to push against the elastic sides of the balloon, and it's going to keep it firm. So every gas exerts pressure on its surrounding, and this definition is expressed mathematically as equaling force divided by area. Now, for a given force, the smaller the area over which that force is exerted, the higher the pressure. And that makes sense because pressure and area are inversely related. Now, the SI unit for pressure is the Pascal, and it's equal to newtons per meter squared. So in other words, 1 Pascal represents 1 Newton of force exerted over 1 square meter of area. What's also important to note is that we're going to encounter different units of pressure, and we need to be comfortable and knowledgeable about how to convert between these different units of pressure. Common units of pressure that you're going to encounter include Pascal, bar, torr, millimeters of mercury, and atmosphere. Please spend some time familiarizing yourself with these units. Now, 1 atmosphere is equal to 101,325 pascals. 1 atmosphere is also equal to 760 millimeters of mercury, and 1 atmosphere is also equal to 760 torr. In addition, 1 torr equals 1 millimeter of mercury. Now, the next thing we want to cover is, well, how do we measure pressure? There are 2 instruments that we want to discuss that measure pressure. The first one is the manometer. This is an instrument that's used to measure the pressure of a gas in a closed container. One type consists of a container of gas attached to a glass U-tube that's open to the atmosphere. So this tube is partially filled with liquid mercury, and the mercury responds to the pressure that's exerted by a gas in the container on one side and then the atmosphere on the other side. The second instrument is the barometer. Now, this is used for measuring atmospheric pressure. It consists of a long glass tube that's closed on one end and filled with mercury. So the setup looks something like this. To start the measurement, the open end of the tube is temporarily covered and then inverted and placed in a reservoir of mercury. Then when the cover is removed, some mercury flows out into the reservoir, but a column of mercury remains in the tube. Now here's how atmospheric pressure plays a role in this. The space above the mercury column in the tube, this is essentially a vacuum. There's no air. So there's no pressure pushing down on the top of the mercury column inside the tube. However, atmospheric pressure is pushing down on the surface of the mercury in the reservoir. And it becomes a balancing act of forces. The weight of the mercury column inside the tube creates a downward force due to gravity, and this is balanced by the atmospheric pressure pushing on the reservoir. If the atmospheric pressure increases, it pushes more mercury up into the tube. And if the pressure decreases, then the mercury levels drop. And the measurement looks something like this. The height of the mercury column in the tube is measured in millimeters, and the height corresponds to the atmospheric pressure. So standard atmospheric pressure at sea level is often cited as 760 millimeters of mercury. Beautiful. Now that we've defined temperature and volume and we have really dived into pressure, next we want to discuss our 4 simple gas laws. To begin, there are 4 variables that describe the physical state of any gas. Those are pressure, temperature, volume, and number of moles. Now, understanding the relationships between these variables is crucial, and that can be explored through the 4 simple gas laws. We're going to start off with Boyle's law. Now, the first observation of the relationship between these variables was actually made by Boyle. Boyle's law states that the pressure of a gas is inversely proportional to its volume when temperature and the number of moles of gas are kept constant. This means if the volume of a gas is reduced, the pressure of the gas increases. And if the volume increases, then the pressure decreases. So again, there is an inverse relationship between pressure and volume. Now, this relationship is represented as a hyperbolic curve on a pressure versus volume graph. And mathematically, this relationship can be expressed as P1V1 equals P2V2, indicating that the product of the initial pressure and volume is equal to the product of the pressure and volume after a change, again, provided that temperature and number of moles remains constant. Next up is Charles' law. Charles' law explains that the volume of a gas is directly proportional to its absolute temperature, provided that the pressure and number of moles of gas are constant. So here, if the temperature measured in Kelvin increases, so does the volume, and vice versa. This law suggests a straight line relationship on a volume versus temperature plot when the temperature is in Kelvin, indicating that the two quantities change in the same proportion. Now, Charles' research also led to the understanding that minus 273.15 degrees Celsius corresponds to 0 Kelvin, and this is the basis for the Kelvin scale, also known as absolute temperature. Now, Charles' law can be mathematically formulated as V1 over T1 equaling V2 over T2. Avogadro's law is next. This states that the volume of a gas is directly proportional to the number of moles when temperature and pressure are kept constant. So if the amount of gas in moles increases, the volume increases proportionally, and this linear relationship can be plotted as a straight line on a graph of volume versus the number of moles. The mathematical expression of Avogadro's law is V1 over N1 equals V2 over N2. Last but certainly not least, we're going to cover Gay-Lussac's law. This law states that the pressure of a gas is directly proportional to its absolute temperature when the volume and the number of moles remains constant. Now, this implies that an increase in temperature will result in a proportional increase in pressure. On a pressure versus temperature graph, this is shown as a straight line, affirming the direct relationship between the two. And the mathematical formula for Gay-Lussac's law is P1 over T1 equals P2 over T2. Now, this background information is going to let us segue into the third objective, which is going to be on the ideal gas law and its applications. Now, we can take three of our simple gas laws, Boyle's, Charles, and Avogadro's, and express them in a way that shows the relationship between volume on the one hand and pressure, temperature, and number of moles on the other hand. So here for Boyle's law, we know that there is an inverse relationship between volume and pressure. And here A is just a proportionality constant. For Charles' law, we know that there is a direct relationship between volume and temperature. B again is a proportionality constant. For Avogadro's law, there is a direct relationship between volume and number of moles. C here is a proportionality constant. Now we can take these three relationships and combine them together. What we get is that V is equal to ABC multiplied by NT over P. Now A, B, and C are constants, and that means their product is also a constant, and we're going to write that as the variable R. This is what we call the combined proportionality constant, also known as the universal gas constant. Now, when we replace ABC with R and we go ahead and move pressure over to the other side here, what we get is our familiar ideal gas law, PV equals nRT. Pressure multiplied by volume equals number of moles multiplied by temperature multiplied by the universal gas constant. Now, R has the following units. It is equal to 0.08206 liters times atmosphere over moles times Kelvin. Now, there is another version of R with different units that you should be familiar with for the MCAT. R can also be equal to 8.314 joules per Kelvin times mole. So you should know both of these variables for R. Now, I want to talk about these conclusions a little bit more. The ideal gas law, let's look at this, PV equals nRT. This is an equation of state for a gas, where the state of the gas is its condition at a given time. Now, if we know three variables, any three variables, we can determine the fourth using this equation. A particular state of a gas then is described by its pressure, its volume, its temperature, and the number of moles. And again, knowledge of any three of these properties is enough to completely define the state of a gas, since the fourth property can be determined from the equation for the ideal gas law. Now, it's also important to recognize that the ideal gas law is an empirical equation. It is based on experimental measurements of the properties of gases. A gas that obeys this equation is then said to behave ideally, and the ideal gas equation is then best regarded as a limiting law. It expresses behavior that real gases approach in conditions of low pressure and high temperatures. Therefore, an ideal gas is a hypothetical substance. However, most gases will obey the ideal gas equation closely enough at a pressure below 1 atmosphere that only minimal errors actually result when you assume ideal behavior. Now, unless you're given information to the contrary, you should assume ideal gas behavior when you're solving problems involving gases in this course. Now, one type of problem that we can encounter involves a gas undergoing changes in its conditions. So in other words, suppose that a gas goes from state 1, where it's defined by the variables P1, V1, N1, and T1, to state 2, which is defined by the variables P2, V2, N2, T2. We can relate these states mathematically. How? Well, we can rewrite the ideal gas law for each state to equal the gas constant R. So for state 1, we can write that R is equal to P1, V1 over N1, T1. And we can write for state 2 that R is equal to P2, V2 over N2, T2. Since both states are now equal to the gas constant R, they can additionally be related to each other, and we can write the following combined gas law. This is going to be extremely useful for problems that involve a gas undergoing changes in its conditions and solving for some initial or final variable. Now, the last thing that we want to cover before we jump into some practice problems is how we can rewrite the ideal gas law using molar mass and density. We're going to first start off by writing molar mass. Molar mass is equal to mass divided by mole. Now, if we shift the variables around, we can write a definition for moles. Moles is equal to mass divided by molar mass. Now, our ideal gas law is PV equals nRT, and we're going to go ahead and replace moles with the definition mass divided by molar mass. Now we have PV is equal to mass divided by molar mass multiplied by RT. The next thing we want to do is rewrite this expression, move around variables so that we have an equation where one side is molar mass and the other side of the equation is all the other variables. So how are we going to do this? We're going to multiply both sides by molar mass. So then we get rid of molar mass on this side, and now we have molar mass multiplied by pressure and volume is equal to mass multiplied by RT. The next thing we're going to do is divide both sides by PV, by pressure and volume. Now we get that molar mass is equal to mass multiplied by RT over PV. Now here's something that's really cool. Mass divided by volume is equal to density. So we can go ahead and rewrite mass over volume as density. And what we get is an equation that says molar mass is equal to density multiplied by the gas constant and temperature divided by pressure. There we have it. Let's go ahead and jump into our first practice problem now. This first example asks, what volume would 12 grams of helium occupy at 27 degrees Celsius and at a pressure of 380 millimeters of mercury? The first thing that we want to do is list out what we know and what we're trying to figure out so we can determine what equation to use to solve this problem. Now we're given temperature, 27 degrees Celsius. We're also given pressure, that's 380 millimeters per mercury. We're given the mass, we have 12 grams of helium, and it's really important to know that we're given the identity of the substance in addition to the mass, which means we can easily also figure out the moles of helium. What are we trying to figure out? We want to figure out the volume. So looking at what we have and what we're trying to figure out, we can go ahead and use our ideal gas law, PV equals nRT. And also remember that R is a gas constant. We know the value for R. It is 0.0821 liters times atmosphere over moles times Kelvin. Okay, now that we know we're going to use the ideal gas law and we've reminded ourselves what the value of R is and what the unit of the gas constant is, now we can begin to convert some of the values we're given into the appropriate units so everything cancels out and we get our final answer in units of liters. So here, the first thing that we're going to do is we want to convert temperature to Kelvin. We're told that we have 27 degrees Celsius. To convert to Kelvin, we just need to add 273. This gives us a temperature of 300 Kelvin. So we can go ahead and write 300 Kelvin. Now the next conversion we need to do is for pressure. So we're given that pressure is 380 millimeters of mercury. We want it to be in units of atmosphere. So we can convert this to atmosphere by using the relationship. 1 atmosphere is equal to 760 millimeters of mercury. Now this is an easy multiplication and division problem here. We essentially have 380 divided by 760, and that is going to equal 1/2 or 0.5 atmosphere. Wonderful, so now we can write that down, 0.5 atmosphere. Now the last conversion we need to do before we start plugging in values is converting our mass of helium into moles of helium. So we are given that we have 12 grams of helium. We can convert this to moles by using the molar mass of helium. 1 mole of helium is equal to 4 grams of helium. And so what we essentially have here is 12 divided by 4, which is equal to 3. We have 3 moles of helium. Beautiful. Now we have everything we need to solve for volume. So the next thing that we're going to do is we're going to rearrange our ideal gas law equation so that we have volume equals all the other variables. That's going to be volume is equal to nRT over pressure. Let's go ahead and start to plug in values. N is moles. We know that we have 3 moles of helium. R is our gas constant. That's equal to 0.0821 liters times atmosphere over moles times Kelvin. And then T is temperature. That is equal to 300 Kelvin. Now that's all going to be divided by our pressure, which is 0.5 atmosphere. So that is what's going to be our volume. Now let's go ahead and try to calculate this. We have 3 times 300, that's equal to 900. And then we can multiply this by 0.08. Now what's 8 times 9? 8 times 9 is equal to 72. All right, then we have these 2 zeros, and then it's really important for us here to make sure that we move our decimal place 2 places down to the left. And so our answer here is going to be 72 for the numerator, and that is going to be divided by 0.5. Now 72 divided by 0.5 is going to be equal to 144. That is our volume, 144 liters. Beautiful. Let's do our second example. This example says, what is the density of carbon dioxide gas at 2 atmosphere and 273 degrees Celsius? So what we know now is that we have a pressure of 2 atmosphere. We have a temperature of 273 degrees Celsius. We also know that we have carbon dioxide. We have the identity of our gas, and we are asked to figure out the density. Now, what we can use here to solve for this problem is our rewritten ideal gas law equation with the variables molar mass and density. We said that molar mass is equal to density multiplied by RT over pressure. Now, we can rearrange this expression so that we have density on one side and all our other variables over to the other side. We get that density is equal to molar mass times pressure over RT. Now again, our gas constant R is equal to 0.0821 liters times atmosphere over moles times Kelvin. Now we have our pressure in atmosphere, so we do not need to convert it, but our temperature is in degrees Celsius, so we can go ahead and convert it to Kelvin by adding 273, and what we get here is 546 Kelvin. Now, something else that we need to figure out is molar mass. We have our gas constant, we have temperature, we have pressure. We need to figure out the molar mass. Now, this isn't going to be super hard because it's just going to be the masses of the 1 carbon atom and the 2 oxygen atoms of carbon dioxide. Carbon has a mass of 12 grams per mole, and oxygen has a mass of 16 grams per mole, and there's 2 oxygens in carbon dioxide. This is going to give us a total of 32 plus 12, 44 grams per mole. That's our molar mass for carbon dioxide. Beautiful. Now we can go ahead and just plug things into our equation. So here we're going to have density is equal to molar mass, 44 grams per mole, multiplied by pressure, 2 atmosphere, over our gas constant, 0.0821 liters times atmosphere over moles times Kelvin. And then that's multiplied by our temperature, which is 546 Kelvin. Okay, let's take this slow and easy. So our numerator is just 44 times 2, so that's equal to 88. What about our denominator? I'm going to approximate this to 0.08 like we did for the first example problem, and then I'm going to round this to 550. This should be a fairly easy calculation. What we can do is we can first multiply 8 by 55. When we do that, we get 440. And let's not forget to add that last 0 here that we didn't account for when we were doing the quick easy calculation between 8 and 55. We just went ahead and added that 0 up. And now all we have to do is move the decimal 2 places to the left to accommodate for the fact that we're not just multiplying 8 by 550, we're multiplying 0.08 by 550. So that means that in the denominator, we get 44. So now we have 88 over 44, and that's a really easy calculation. That's just equal to 2. And so our density is going to be equal to 2 grams per liter. All right, so that's it. And you can notice that the units are going to be in grams per liter because everything else cancels out. So moles cancels out, atmosphere cancels out, Kelvin cancels out. What we're left with is grams per liter. So the density is 2 grams per liter. Now we did do some approximations. If you went ahead and plugged this in the calculator to see how close your value is to the true answer is 1.96 grams per liter. So we were very close. Awesome, let's move on to our third example. This example says, what is the molar mass of a 22.4 liter sample of gas that has a mass of 225 grams at a temperature of 273 degrees Celsius and a pressure of 10 atmospheres? Let's go ahead and write down what we know. We know that the volume is 22.4 liters. We know that the pressure is 10 atmosphere. And we know that the temperature is equal to 273 degrees Celsius. We also know what our gas constant is. It's 0.0821 liters times atmosphere over moles times Kelvin. And we're also given the mass of this unknown sample of gas. It's equal to 225 grams. Now, you might initially be inclined to use our formulation of the ideal gas law that includes the variables molar mass and density because you figure you're solving for molar mass. So you might want to use this equation. However, please be cautious. This is not the correct equation to use because we don't have any information on density. And we can't figure it out because we actually don't know what this unknown sample of gas is. So this is not the correct equation to use. Instead, let's remember what molar mass is equal to. Molar mass is equal to mass divided by moles. We're given the mass, and we're actually given just enough variables to use our ideal gas law to figure out moles. And that is the tactic we want to use to solve this problem. So we're going to use PV equals nRT to solve for moles first and foremost. Now let's make sure that all our variables are in their appropriate units. Volume is in liters, check. Pressure is in atmosphere, check. Temperature is in degrees Celsius. Let's go ahead and convert that to Kelvin by adding 273. We get 546 here, Kelvin. And now we're good to go. The next thing we want to do is rearrange our ideal gas law so that we have moles equals all our other variables. That's going to give us that moles is equal to PV over RT. Now we can begin to plug in our values. Pressure is 10 atmosphere. Volume is 22.4 liters. Our gas constant is 0.0821 liters times atmosphere over moles times Kelvin. And then our temperature is 546 Kelvin. Beautiful. Now this numerator is easy to calculate. We're just multiplying 10 by 22.4, which gives us 224 in our numerator. And then our denominator is a really familiar calculation that we just did in the previous example, and we calculated it out to be 44. Now we can approximate these values to 225 and 45 to make this calculation a little bit easier, and this gets us 5 moles. All right, and notice that our units are moles, and that's because all the other units cancel out appropriately. So we did our calculation correctly. Now we have moles. We're given the mass. We can calculate the molar mass. The molar mass is going to be 225 grams divided by 5 moles, and this gets us 45 grams per mole. So the molar mass of the gas is 45 grams per mole. So that is example 3. Let's move on to example 4. This example says a 2-liter sample at 100 degrees Celsius and 20 atmosphere contains 5 moles of a gas. If an additional 25 moles of gas at the same temperature and pressure are added, what is the final volume of the gas? So it seems like we have an initial state and a final state for our system. Let's go ahead and write down what we know and what we're trying to figure out. So in our initial state for our system, we know that the volume is equal to 2 liters. the pressure is equal to 20 atmospheres, the temperature is equal to 100 degrees Celsius, and we have 5 moles of our gas. In our final state for our system, after it has evolved, we're trying to figure out the final volume. We know that the pressure and the temperature do not change, so final pressure is still 20 atmospheres, and final temperature is still 100 degrees Celsius. Now, what about our final number of moles? Well, this has changed because we have added an additional 25 moles of gas to our already present 5 moles. So our final number of moles is going to be 25 plus 5, and that is equal to 30 moles. Now we notice no change in pressure, no change in temperature. If pressure and temperature are held constant, the ideal gas law reduces to Avogadro's principle. And Avogadro's principle says N1 over V1, or we can say N initial over V initials equal to N final over V final. All right, we've seen it as N1 over V1 equals N2 over V2. I usually like to use initial and final just to keep things in track. All right, so now let's go ahead and plug in what we know and try to solve for final volume. Our initial number of moles is 5. Our initial volume is 2 liters. Our final number of moles is 30, and we want to figure out final volume. Now, to isolate final volume, we're going to have 2 liters times 30 moles divided by 5 moles. And you notice moles cancel out. Our final answer is going to have units of liter. What's 2 times 30? That's going to be 60. 60 divided by 5 is 12. So our final volume is going to be 12 liters. Let's do this next one. This next example says, what would be the volume of a 1 liter sample of helium if its pressure is changed from 12 atmospheres to 4 atmosphere under isothermal conditions? All right, so isothermal conditions means that temperature is not changing. We're also not given any information about number of moles changing. The only thing that's changing is the pressure, and we're trying to figure out the change in volume with that change in pressure. So we know our volume initial is 1 liter, and our pressure initial is 12 atmosphere. Our final pressure is 4 atmosphere, and we're trying to figure out what our final volume is. So here, if the number of moles of gas and temperature are held constant, then the ideal gas law just reduces to Boyle's law. P1V1 equals P2V2. Now, I just want to say, and this is a note for this example and the one that we just did, if you forget your simple gas laws, or if you don't want to memorize them, there's only one thing then I would recommend you memorize. And that is the combined gas law. The combined gas law says P1V1 over N1T1 is equal to P2V2 over N2T2. And you can get any of the simple gas laws from this relationship when you know what's held constant and what's changing. So for our problem, temperature stays the same. So T1 is equal to T2, so that means we can eliminate that. And number of moles is also not changing, so N1 is equal to N2, so we can eliminate that. What we're left with is Boyle's law, the relationship between pressure and volume. So now let's go ahead and plug in things. The initial pressure is 12 atmosphere, initial volume is 1 liter. Final pressure is 4 atmosphere, and we want to figure out that final volume. We're going to divide both sides by 4 atmosphere so that we can solve for final volume. What we get for final volume is 12. Atmosphere cancels out first and foremost. We have 12 times 1, that's 12, divided by 4, that's 3. And then the only unit that's left is liter. So our final volume is 3 liters. Let's do another one, all right? This example says if the temperature of 2 liters of gas at constant pressure is changed from 290 Kelvin to 580 Kelvin, what would be its final volume? So here we're given the initial volume as 2 liters, and we're given the initial temperature as 290 Kelvin. Then we're told that the temperature changes. The final temperature is 580 Kelvin. What is the final volume? Now, that means that pressure and number of moles are held constant because we're not given any information about those variables changing. So if the number of moles of gas and pressure are held constant, then the ideal gas law reduces to Charles' law. That's going to be V1 over T1 is equal to V2 over T2. And again, if you do not remember Charles' law, you can get it from our combined gas law. Here in this scenario, we know that pressure isn't changing because we're not told that it changes. So P1 is equal to P2, and those cancel out. We're also not told any information about number of moles changing, which means N1 equals N2, and we can go ahead and eliminate that. And what we're left with is Charles' law. So now we can go ahead and plug in what we know. Our initial volume is 2 liters. Our initial temperature is 290 Kelvin. We want to figure out our final volume. Our final temperature is 580 Kelvin. Our final volume is going to be equal to 2 liters multiplied by 580 Kelvin divided by 290 Kelvin. All right, wonderful. Now Kelvin, the unit Kelvin cancels out. Now we have 2 times 580. This is going to give us 1,160 in the numerator. And then we have 290 in the denominator. This is going to be about 4 liters. So our final volume here is going to be 4 liters. All right, one more practice problem before we move into our next objective. This example says if the pressure of a sample of gas with a temperature of 300 Kelvin changes from 2 atmosphere to 5 atmosphere during heating, what would be the final temperature if volume is held constant? Let's go ahead and write down what we know. We know that the initial pressure is 2 atmosphere and the initial temperature is 300 Kelvin. We also know the final pressure, that's equal to 5 atmosphere, and we are trying to figure out the final temperature. We also know that the volume is held constant, and they don't inform us of the number of moles changing. So if the number of moles of gas and volume are held constant, then the ideal gas law reduces to Gay-Lussac's law, which is P1 over T1 is equal to P2 over T2. And again, if you do not remember this simple gas law, that's totally okay. Hopefully, you just remember the combined gas law, and from there, we can extract this relationship. So in this problem, we know that volume stays the same, so V1 and V2 are equal, and we can cancel them out. We also know that moles isn't changing, so N1 is equal to N2, and we can cancel that out, and what we're left with is the same relationship we just wrote down. Now let's go ahead and plug in what we know. The initial pressure is 2 atmosphere, initial temperature is 300 Kelvin, final pressure is 5 atmosphere. We're trying to figure out final temperature. Now let's isolate T final and solve for it. This is going to be equal to 300 Kelvin multiplied by 5 atmosphere, all divided by 2 atmosphere. The units atmosphere cancels out. We're going to get our final answer in units of Kelvin. 300 times 5 is equal to 1,500, and that's divided by 2. And so what we get for our final temperature is 750 Kelvin. Beautiful. Those are all the practice problems we wanted to do before we move into our next objective. We're going to end the video here and continue in the next video. Please let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day, future doctors.